Thank you for joining us on Synthesis Workshop. In today's installment of our Advanced Organic Chemistry course, we're joined by Dr. Dennis Kutateladze. Dennis has previously joined us to talk about his doctoral work on this podcast, and I'd strongly encourage you to check out that talk as well. To briefly reintroduce Dennis, he did his bachelor's degree in chemistry at Cornell University, where he worked in the group of Professor Haining Lin. He then completed his PhD at Harvard in the Jacobson Lab, working on innovative applications of organocatalysis. Currently, he's a postdoc in the Buchwald Lab at MIT. Today, we'll be continuing our core knowledge module in the course as Dennis gives us a talk on chemical kinetics. Thanks a lot for joining us today, Dennis.
Hi everyone. So thank you for tuning in. Before I get started, I just wanted to extend a huge thank you to Matt for having me on the program. I'm really excited to be discussing chemical kinetics, something that I spent a long time during my PhD studies thinking about. So in today's episode, I'm going to cover a couple things divided into two sections here. On the left-hand side, we'll talk about orders when it comes to reactions, some of the typical things you might see in reaction development, first order, zero order kinetics, and something we'll call saturation kinetics at the end. And then kind of woven into those stories, I'm going to tell you about data collection and interpretation using modern day kinetic techniques. So we're going to begin by talking about a reaction, right? And we know that reactions, among many things, obey rate laws, right? And we could write a reaction, a general reaction, A, B, and C react together to make product P, right? Now this reaction occurs with a rate constant K. So we can express the rate of a reaction, any reaction, A, B, and C going to P, generally in terms of derivatives. So in this example, the rate of the reaction is a change in concentration over time. And we can express that rate in terms of A, B, C, or the product P. In the case of the reactants A, B, and C, the rate of the reaction is expressed as a negative change in concentration of that reactant over time. Whereas for the product, it's sort of the opposite. It's the positive. It's the growing in of product P over time. Now, all reactions obey rate laws. That's the title of this slide. And for any reaction A, B, and C, we can express the rate as shown in the bottom here, this rate law. Now the rate law possesses a rate constant, that's K, and then is dependent on the concentrations of A, B, and C. And these concentrations have powers. They're called orders, actually. So by doing kinetics, what we really mean is defining the orders X, Y, and Z. These are numbers that help us understand mechanism. And one of the primary reasons that a scientist might want to study a reaction kinetically is to understand mechanism. So let's go through a simple example to begin here. Now, this sort of scenario actually shows up pretty frequently when it comes to small molecule organic reactions. Here, A reacts to form product D through two steps. Step 1 has a rate constant of K1, and step 2 involves the addition of another reagent, C in this case, and proceeds with a rate constant K2. So now this reaction proceeds through an intermediate B. In one scenario, because this is a multi-step mechanism, we could, on an energy diagram, represent these reactions as shown. On the left would be the case in which the first step in this sequence is rate limiting. And recall that what that means is that the barrier height between the first and second step is the highest for step 1 in this case. Another possibility would be the second step involving the addition of reagent C is rate limiting. In this case, both steps contribute to the overall rate of the reaction, and here it's more appropriate to describe the rate limiting step as a rate limiting span. So the energetic difference between the highest transition state and the lowest intermediate on the reaction coordinate diagram is what we would call a rate limiting span. But regardless, the idea here is that we could use kinetics and kinetic experiments to distinguish between these mechanisms. Now, in a moment, I'll discuss how to derive rate laws and rate equations for these sorts of mechanistic scenarios. But for now, we can appreciate that the rate laws for both of these mechanisms are distinct. On the left, the first step being rate limiting would necessitate a first order dependence on the concentration of the starting material A. However, in the second mechanistic scenario, we would see an order dependence on C. Now, we'll explain why this is a little bit more complicated, but the presence or absence of an order can also be used, at least in this case, to distinguish between different mechanistic possibilities. All right, so now the question becomes, how are we able to use experiments to assign orders in a rate law for a given reaction? So we could come back to our model reaction A, B, and C going on to form product P. And again, recall that the rate law in this case is comprised of a rate constant K, as well as A, B, C, raised to the powers, in this case, X, Y, and Z. Now, to experimentally determine the orders X, Y, Z in components A, B, and C, we could perform an analysis that's called initial rates kinetics. Now, this is a really popular way to perform kinetic analyses. I would say that most times in articles published today, this is sort of what's done. There are a lot of advantages. We'll talk about it in a minute, but the idea here is that what if we were able to reduce the complexity of the problem? That is, could we assume that this first term, K, A, B, and C, is actually a constant number, right? Now, that might sound sort of outlandish. However, in the early stages of a chemical reaction, it turns out that the concentrations of the starting materials are not changing appreciably. So in this scenario, the product of the true rate constant and the concentrations of the reacting components in this scenario raised to their orders becomes a constant number, and we call that constant number K obs, or the observed rate constant. So solving this differential equation in terms of A yields the following result. We see that the concentration of component A displays a linear relationship with respect to time t, and the slope of a plot of the concentration of A over time should provide us with K obs. Now, I've done this example for component A, but it turns out that every component in a chemical reaction can be expressed this way. So it works for B and C, as well as product P, and it's always the same sort of result here. So we've always reduced it to a linear equation. Now, it's important to note that this sort of analysis really only holds for the first maybe 10% conversion in a reaction. And again, that's for the reason that as a reaction proceeds, the concentrations do start to change. However, in the early stages of a reaction, you really can get away with this sort of analysis. And I'll show you a comparison later in this presentation that hopefully will illustrate that. So what we're looking for is a way to obtain the value of the observed rate constant, K obs. So what that really means is we'd like to be able to measure concentration over time for a chemical reaction. And ideally, we'd like to be able to do this for different components in the reaction. So in principle, if we had a way to measure concentration over time, we could get the order in any of the reaction components by following their conversion over time independently. So we could do this by a variety of spectroscopic means, including REACT-IR, which is a device that measures IR spectra in a time-dependent manner. We could also look at time-dependent NMR spectroscopy or other things, but these sorts of analyses would provide us with a way to monitor concentration over time for different components. Now, the object here would be to start with different initial concentrations of the component that we're interested in obtaining the order in. So in this example, we'll look at the order in component A, and I've simulated some data here that will hopefully help us understand how to perform an initial rates workup. So we see three traces. The blue, red, and green traces here all begin with different initial concentrations of component A. Now, what we do is we simply fit the first several data points, and as I mentioned previously, usually 10% or less conversion for these different initial starting concentrations of, in this case, A. Now, recalling what we learned on the previous slide about initial rates, the slope of that fit turns out to be the observed rate constant. Now, what we can do is generate a plot that expresses the observed rate constant against the initial concentration of the component we're interested in identifying the order of, in this case A, and we'd like to raise that to different powers. The idea here is that we can manipulate the identity of the power n that then results in a linear relationship between the observed rate constant and the concentration of, in this case, A. Now, the value of n that results in a linear relationship is the order in component A. So we see here we could fit these data to A to the second power on the right, but we see a linear fit on the left here. So we could easily do this for other components in a reaction, sort of simulated what it would look like if component B were a second order dependent. So this sort of approach is agnostic to the actual order in the component of interest. So with this data in hand, what our conclusion would be is that the reaction of interest is a first order dependence on the concentration of A and exhibits a second order dependence on the concentration of B. This would provide us with an empirical rate law that has the form shown here. We'd raise A to the first power and the concentration of B to the second power. Now, if we come back to that data that I had simulated earlier, and we use the actual rate constants that are extracted from the slopes of the fits, we do indeed see that these data are first order, and that's sort of a nice sanity check. So we see that linear relationship between K-obs and the initial concentration, A naught here. All right, another sort of interesting kinetic outcome could be what's known as zero-order kinetics, or that the rate of the reaction does not depend on the concentration of the component that we're looking at. This actually happens relatively frequently, and a lot of times what it means is that the component that we're looking at simply doesn't appear in the rate-limiting step of the reaction. And I'll talk more about this later, but this is something that is also definitely good to keep in mind. Now, initial rates kinetics are clearly quite powerful means to define a rate law empirically, and that's for the reason that they're quick and easy to perform. There's not a lot of high-level mathematics that goes into thinking about this. It's sort of easy to draw conclusions about reaction mechanisms in a short amount of time. However, nothing's without limitation, of course, and one possibility is that it might not be super straightforward to start fitting points, especially in reactions that are quite fast. It can be difficult to achieve meaningful initial rates. But the more important thing is that sometimes reactions behave very differently in the early stages as compared with different stages of the reaction. This actually happens pretty often in catalysis, where the first turnover exhibits a different rate law than the rest of the reaction. So to think about getting a more accurate representation about the kinetics of a reaction, we could perform an analysis that's called whole rate kinetics. And really what that means is we're going to derive the orders in reaction components not just from the first several percent, but using the entirety of the reaction. Now what this would involve fundamentally is using the entire concentration versus time profile and turning that into a rate. What we'd really like to be able to do is convert concentration versus time data into rate versus concentration data to access what we would call a graphical rate law. How does the rate depend at every point in the reaction on the concentration of A in this case? In order to do that sort of analysis, what we'd really like to be able to do is, again, have a good way to measure concentration versus time, but we'd also need to transform it somehow. And the way that we would be able to do that is by fitting the concentration versus time data to a mathematical function that we know we can take the derivative of with respect to time. Then we take that derivative, provides a rate, and we can plot that against the concentration of, in this case, A, and obtain that graphical rate law. So the graphical rate law here is important because, again, it expresses how the rate is affected by the concentration of A over the course of the entire reaction. So we get this sort of nice readout that takes into account the entire reaction and not just the first couple percent. So to begin with this sort of analysis, we need to identify functions that fit concentration versus time data. And one way to identify such functions is by solving the differential equation for a given mechanism to provide what we would call an integrated rate law. So as an example here, we'll begin with first order kinetics. And again, this is something I would say that we encounter pretty frequently experimentally. So I have the mathematical treatment on the slide on the left here. And remember that we can treat the rate of a reaction as a change in the concentration of A, in this case, over time. So I've rearranged that equation such that the time component of the derivative appears on the right, whereas the concentration component appears on the left. Now what we can do is integrate both sides over all time, and then we're left with the following expression that shows the concentration of component A as a function of time t. So what this data is telling us is that a first order decay in compound A should fit an exponential function. So back in graduate school, I worked on one project that involved such a treatment, and I want to go through some of the details here as an example. So the reaction that I was looking at was a hydrogen bond donor catalyzed cyclization of compound 1B, in this case an allylic chloride, to provide access to a carbocycle in an antinumerically enriched form. Now, when we looked at the kinetic profile of this reaction by following the concentration of 1B, in this case the starting material, over time, we were able to identify that just from the fit, we could fit an exponential function to those data quite well and obtain kinetic parameters just from that. So we, again, could verify that this reaction possessed a first-order dependence on component 1B. But how do we take that exponential fit and turn it into a graphical rate law, right? How do we get the rate against substrate concentration? So luckily, the derivative of an exponential function is almost exactly the same form. We just move the exponent down, and we're able to use that differentiated function as a way to express rate. And in doing so, we end up with a plot that displays rate against the concentration of the substrate. So the fact that the plot between rate and substrate concentration is linear tells us two important things. The first is that there's a first-order dependence of the reaction rate on the concentration of 1B. That's because 1B on the x-axis is raised to the first power, and we see a linear relationship between rate and 1B, much like the sort of approach that we used earlier for initial rate kinetics. But the fact that it's linear throughout the entirety of the reaction also tells us something important, which is that the rate law does not change. Now, sometimes the rate dependency on a specific reaction component can be a little bit more complicated, and it's also a good idea sometimes to fit concentration versus time data to unbiased functions. One of the best unbiased functions that I've found, at least in my own experience, are n-ordered polynomials. Polynomials are great functions because they're also quite simple to take the derivatives of. And I just wanted to make a point that in this report, we also looked at a polynomial fit to the data, and you can see that the fits are good too. All right, so another useful comparison that I want to draw here is between initial rate kinetics and whole rate kinetics for the same data set. So what I've shown here is that decay in the substrate 1B, the concentration over time, and what we can do is compare the result that we get from initial rate kinetics to this whole rate kinetics approach. So in the initial stages of the reaction, according to the whole rate kinetics approach, we find that the rate is approximately 1.5 times 10 to the negative 5 molar per second. Now, how does initial rates stack up against that? Well, it turns out that it's dependent on the number of data points that we select. So I feel bad about selecting less than 4, typically for a linear approach, so we'll start at 4. And if we compare 4, 5, and 6, and again, recall that the k-obs is the slope of the linear fit, we find that in 3 cases, we achieve a pretty good agreement with the initial rate that's provided by the whole rate kinetics approach, with under 10% deviation between these two approaches. That's good news because it tells us that initial rates is reliable in this case. But I did want to make a point that whole rate kinetics can still offer some pretty significant advantages outside of just being able to tell us that the rate law doesn't change over the course of the reaction. I want to talk briefly about an experiment that I find to be quite informative. This is a type of experiment that was developed by Donna Blackman's group, and it's called the same excess experiment. The idea here is that we can actually observe the rate dependence of a reaction at different stages and make sure that they overlap. This is an experiment that's designed to probe for catalyst decomposition or product inhibition throughout a reaction. Now, there's a really good reference that I provided in the bottom, and I'd really encourage you to look further into that. But I wanted to note that we performed this sort of analysis in our case, and starting the reaction, a full equivalent of substrate versus half an equivalent of substrate with all of the other concentrations unchanged provides good overlap. So what this tells us again is that the reaction is well behaved in that it does not experience catalyst decomposition or product inhibition. All right, so we just talked about first-order kinetics, and we briefly touched on zero-order kinetics earlier in this presentation, but I want to go through what the integrated rate law for a zero-order kinetic reaction would look like. So if we were to monitor concentration over time for component A that exhibits a zero-order dependence on the reaction rate, we'd actually find that we see a straight line with slope k, which is the true rate constant. And we can appreciate this through the same sort of procedure that we used previously with the first-order kinetics. Now, in this case, the rate of the reaction is expressed as the rate constant times the concentration of A to the 0th power, meaning just K. And again, integrating both sides, we can solve the differential equation over all time and achieve the following result, that the concentration of A is expressed linearly over time with, again, the slope of the line being the rate constant. Now, one thing I wanted to talk about is, how is it possible for a reaction to exhibit a zero-order kinetic dependence on a reactant that is required for the reaction to take place? That might seem like sort of unintuitive. Well, one possibility, and this is, again, usually the situation, is that the reagent in question is involved in a post-rate limiting step. So if we come back to our initial example on the first couple slides, we would expect to observe a zero-order dependence on component C if the first step in this sequence is rate limiting, for the reason that the kinetic experiments are only able to capture events that take place within the rate limiting step or span of a chemical reaction. There, of course, are other possibilities, and another scenario would involve mass transfer being rate limiting due to poor solubility. This sometimes happens in biphasic reactions. And the last possibility is an interesting concept called saturation kinetics. And I want to spend the last moments of this presentation discussing what saturation kinetics really are. So saturation kinetics occur when the order in compound A, for example, is dependent on the initial concentration of A. And we see canonically several different regimes. For low concentrations of A, we see a first order dependence, right? And you can see this sort of by looking at the graph here. And it starts to sort of level off for higher concentrations of A. So we sort of proceed from a first order dependence to a zero order dependence. And usually what this sort of effect has to do with fundamentally is a binding interaction. Now, I think it's sort of interesting to start thinking about this in the context of catalysis, because saturation kinetics usually only happens in catalytic conditions. And we'll touch on these momentarily, but hopefully to appreciate saturation kinetics, we can begin by considering a multi-step mechanism with a reversible first step. So here, component A is transformed into product P through two distinct steps. A first step consisting of a reversible event that gives rise to intermediate INT in green, followed by a subsequent step that transforms the intermediate into the final product. And I've listed the rate constants for those steps in the equation. Now in this case, the rate of the overall reaction can be expressed as follows. The rate is equal to the second rate constant, K2, times the concentration of the intermediate. But now a problem arises, which is that the concentration of the green intermediate is likely not something that we can monitor easily. It might be sort of high in energy, and it might be fleeting, or it might be present in very low concentrations. So it can be very difficult, or in some cases impossible, to actually measure the concentration of that intermediate accurately. So in this sort of scenario, we actually have to estimate the concentration of the green intermediate, which involves approximations or assumptions. And the one that I'll touch on today is what's known as the steady state approximation. The steady state approximation, simply put, is this idea that the change in concentration of the intermediate over time is equal to zero, so that essentially the concentration does not change over the course of the reaction. Usually it's valid to make this sort of assumption because intermediates can be very high in energy and fleeting. So it turns out that the steady state approximation can be used to derive rate laws for common kinetic scenarios in catalysis. Going back to the first example that we just saw on the previous slide, the intermediate that we could be talking about actually could be a catalyst-substrate complex, which occurs quite frequently in catalysis. Now here the idea is that component A binds to catalyst C in a reversible step to generate intermediate I in this case, and that intermediate is then transformed to product P with rate constant K2. Now here we're assuming again that the concentration of I is small and that it disappears essentially as quickly as it is generated, which are the sort of central facets of the steady state approximation. Now here we can define the rate as the product of the second rate constant K2 and the concentration of intermediate I, but recall that we don't have a good way to measure the concentration of I directly. In fact, what we have to do is express the concentration of I in terms of observable quantities in the reaction. That is the concentration of substrate A and the initial concentration of catalyst. Now, applying the steady state approximation again means that the concentration of the intermediate I does not change over the course of the reaction, so we set that to zero. And then we can define all of the elementary processes that occur that affect the concentration of intermediate I. In this case, there are three of them. The first process is the binding between catalyst C and substrate A. that possesses a rate constant K1. So we can denote that K1 multiplied by the concentration of A and multiplied by the concentration of catalyst C. Now we subtract the processes that deplete the concentration of intermediate I, that is the debinding interaction with rate constant K minus 1, which of course is also dependent on the concentration of I, as well as the productive reaction, which takes place with rate constant K2. Now here we could simply solve for the concentration of I, but we'd be left with an expression that's in terms of the concentration of catalyst C. And again, we can't measure that directly because the concentration of catalyst C feeds into a larger expression. The initial concentration of catalyst C is actually the sum of the free catalyst C as well as the concentration of the intermediate I. So here we can solve for the concentration of free catalyst C through that simple relationship and then plug that back into the original equation that we used for the steady state approximation. Now through some manipulations we can determine or express the concentration of I, the intermediate, in terms of A as well as the original concentration of the catalyst, or the total catalyst concentration, which is shown on the bottom. Finally, putting the expression for the concentration of I back into the original rate equation provides the following result. Now, one thing to notice about the form of this rate equation is that the concentration of A appears both in the numerator and the denominator. What this tells us is that the sort of order in A is concentration dependent. Now we can consider how this might be the case if we take the limiting scenarios for low concentrations of A and high concentrations of A. So at low concentrations of A, we find that the denominator reduces to the sum of the two rate constants K minus 1 and K2. So effectively, the rate displays a first order dependence on the concentration of A as well as the concentration of the catalyst. However, something interesting happens at high concentration of A. Under these conditions, the denominator of the rate expression becomes equal to K1 times the concentration of A. So overall, what this means is that the rate expression reduces to the product of the second rate constant, K2, and the initial concentration of catalyst. So this is a zero order dependence on A. So we can appreciate this graphically, coming back to that first plot that I showed earlier. Now, what does this mean for an energy diagram? We can start to rationalize this behavior by thinking about what's actually happening at the molecular level. Now on the left, a first order dependence on A means that the intermediate, the complex between A and C, is higher energy than A by itself, which again is a pretty common scenario. In this case, we have a rate limiting span that involves the binding step between A and C as well as the high energy step that converts A to P with the rate constant K2. However, on the right, we can insert enough A into the reaction mixture that the binding event becomes thermodynamically favored. And what this does is it shifts the complex AC, that intermediate, to lower energy, such that this is now an intermediate that builds up. Now, adding more A to the reaction mixture is not going to speed up the reaction because the reaction is governed by the catalyst. So when all of the catalyst is tied up in a complex with A, that means that the catalyst is what we would call saturated. And hence we see a zero order dependence on A because it doesn't factor into the rate limiting step, which in this case becomes step 2. So step 1 has no effect on the rate of the reaction. We could also depict this sort of scenario using a catalytic cycle. In the top here, again for low concentrations of A, we see a first order dependence on A. So the first step is effectively reversible. Now the resting state of the catalytic cycle involves the 12 o'clock position. Here, the catalyst is unbound to A, and it's energetically uphill to access intermediate AC. However, for high concentrations of A, we see the resting state of the catalytic cycle is shifted to the 6 o'clock position. That is, the intermediate builds up and becomes the resting state. Recall that the resting state for a catalytic cycle is the lowest energy point on the catalytic cycle that involves the catalyst. All right, with that, I just wanted to conclude by saying that I think that kinetic analysis is a very powerful tool that we can use to think about reaction mechanisms. And again, there are several approaches that we touched on today, using either initial rates or whole rates. And it turns out there's so much that you can do with the insight that's provided by kinetic analysis. And hopefully this presentation has illuminated some of those. So thank you again to Matt for the opportunity to present. And please feel free to post any questions you have in the comments section.
Thanks, Dennis, for a great talk on kinetics. Tune in for our next episode where we'll finish our core knowledge module and continue this advanced organic chemistry course. See you next time.